Hello, welcome to Sage Math class. Today we are going to discuss a problem to find the tangents to a given curve. Find the this is the question. Find the horizontal tangents of the function fx equals square root of 2x raised to 4 minus 2x plus 1 over 2x raised to 4 plus x plus 1. I mean the inner expression is inside the square root symbol we have the expression 2x raised to 4 minus 2x plus 1 in the numerator and 2x raised to 4 plus x plus 1 in the denominator. See, let's see the outline of the solution of this problem. We first compute the derivative of the given function. F is the given function. We first compute the derivative of the function. Some chain rule is used to obtain the derivative. Okay, it's because it's a function of function. You have to treat it as a function of function, but the system will itself do that applications of chain rule. Now we have a simple method to obtain the derivative, that is just to type the command diff and use the given function inside the bracket together with the simplify command dot simplify underscore full. So this will simplify that expression which is obtained after differentiation. But in the first step you have to define the function fx equal to square root. To say that we want to find the square root, so we use for that we use sqrt function. So fx equal to sqrt, then in bracket 2x raised to 4 minus it's then that numerator part is written 2x raised to 4 minus 2x plus 1, and then it is divided by 2x raised to 4 plus x plus 1. Okay, let us now try it with the Sage Math system. So going to the Sage Math input cell. Okay, you can just copy that function. You can copy the function and then paste it. Okay, let's check whether there is any error. Okay, there is no error. Now the function has been defined. So if some other function is given to solve a similar kind of problem, you have to then you have to first find you have to define the function. You have to tell the system and the Sage Math system that this is the function. So for that purpose, this is that the step used. Okay, next next step is to differentiate that function and then to express it in the in simple terms. Okay, that is then substituted. Next, after typing that, you can take the output. You can see that sometime it will take, the system will take some time, but yeah, now we have obtained that output. You can read that output 3 over 2 into in bracket 6 into x raised to 4, 6x raised to 4 minus 1 divided by the denominator part is denominator part contains a lengthy expression. Okay, you can just compare it with the solution available in the manual. Okay, you can then see that the same function is obtained there, so it indicates that there is no error. Okay, now what next? Thinking about the next step, we want to find the value, the solution of the derivative when we can make an equation using this derivative, equating it with 0, and then we will try to solve it, because the values of x which satisfies which satisfies the different derivative of the given function. We know that the derivative of the given function stands for the slope of the tangent at a point on the curve. at a given point on the curve. So you think about a point on the curve. At that point you can draw a line which touches the curve and passes through that point. If that curve is drawn, then you can find the slope of that. If after drawing that line tangential to the curve, you can obtain the slope of the that tangent. Slope of the tangent, and the slope of the tangent can be obtained. But in this problem, that is the general situation. So far we have explained the general situation that explains the meaning of the derivative of a given function in calculus. But in this case it is asked to find the horizontal tangents of the function. Horizontal tangents of the function. So it means what is meant by the horizontal tangent? And that's a tangent which is parallel to the x-axis. So a horizontal tangent is parallel to the x-axis. So if there exists such a we don't know at this moment, we don't know whether there exists a tangent, a horizontal tangent, but if that exists, you can easily say that the slope of that tangent equal to 0. It's because it is parallel to the x-axis. See, since the horizontal tangent is parallel to the x-axis, the slope of the tangent must be equal to 0. So if this curve, if the given curve, if the given function has some horizontal tangent, then those values, the corresponding values of the slope, the corresponding values of the slope of those tangents must be obtained by solving the derivative of the given function, equating it with derivative by solving the derivative of the given function after equating it with a 0. So this is the next step. So we get this this statement you can write here. You can see that we take the derivative of fx and then it is equal to 0. After obtaining that equation, then we get an equation, and that equation can be solved to obtain the respective value or the corresponding value of x. It is then solved to obtain the corresponding value of x, and then that value of x will give us the tangent, the slope of the tangent equal to 0. Okay, then we can next go to implement that step in SageMath. So that is this type, and then you take the output. You can see that the 4 different values of you can see 4 different values of x are displayed there. First value this one, and second value, third value, and fourth value. And of these 4 values, and 2 of the values are negative, are complex values. That can we understand that the presence of I, the first in the first number, in the first value obtained for x, you can see I present. Also in the third one obtained, you can see this I, so minus 1 by 6 into I into 6. So these are the 2 complex roots of that equation. We don't want that complex roots because we are not considering the complex plane. Here we are considering the real axis of x and y axis. So we are not interested in complex roots, complex values which are obtained as roots. Okay, therefore we shall move to the next step by accepting only the second and the fourth value, which are real values, real numbers. Okay, you can see that answer here displayed, but you can compare it with that, and therefore by selecting those 2 values, the 2 values which are real values, that is the second value, and then you can simplify it. Similarly, you can simplify the last value to obtain the slope of the tangents, which are parallel to the x-axis, or slope of the horizontal tangents. Next we want to confirm confirm this computation, we want to make it more clear by geometrically by referring a figure. So for that, we are going to plot this curve, or plot a curve of the given function with x as the variable. It will be plotted considering x as the variable, and for plotting purpose we are considering the values of x between -2 and +2. So we have to write the command as g is equal to g stands for the plot which is obtained here. G equal to plot of we write g equal to plot of fx comma x, then -2 2, and then figure size equal to 3. Okay, you can just copy it and paste it in the input cell, and you can by this command we can obtain the plot. We can create the plot, and that can be stored at g, at the location of g. But in order to take the output, take the figure as an output, you have to type g again and take the output. And before taking the output, you have to type g again, and then you just type the command, or just press the keys to take the output. Now you can see that this is the curve, a nice curve you can see, and that curve you can see from x theta, it stretches from -2 to +2. It's available from -2 to +2. Okay, and that's a continuous curve, and there you can see that when we analyze the appearance, when we analyze the physical nature of the curve, you can see it starts at some point, and then it increases its value at some point of y, and it increases its value and reaches a maximum. After reaching there, it then gradually comes down and reduces its value until it reaches a lowest level, and where from there it then again increases, and we don't know what happens beyond the point, beyond the limit x equal to 2. But it is not a very serious thing, but we just want to say, or to find the points where the horizontal tangents exist. Now you can see, due to this peak position and this the lowest position, this highest position, and you can see that at this point you can draw a tangent. When we draw, actually you can draw tangents at every point on the curve, but if we draw the tangent at this point, that will be parallel to x-axis, so it is a horizontal tangent. Similarly, here you can, at this lowest point, you can draw, when you draw a tangent, that will also be parallel to the x-axis. So this is the by this we come to the end of the solution of the problem. Okay, thank you.